Now we're going to look at calculating Jacobians for a couple of simple arm configurations. The first one being a radial polar arm. So here's the arm. It's got a joint at the bottom. It can move around through an angle theta, and the link length is r, right? So it's easy to write from first principles down the forward kinematics of this, so we want to know what the endpoints are in terms of r and in terms of theta. And we're not saying here that r is fixed. It could actually be that it's something that could be extended as well. So let's leave that opportunity open and treat it as something that could vary. So let's think about the Jacobian matrix. For this, it's going to have 4 parts because we've got x and we've got y. So we have effectively got 2 functions. And we see the functions depend on theta, and they also depend on r. So we need to calculate 4 elements for our little tiny Jacobian. First of all, for the function at the top, it's going to be delta x with respect to delta theta, which is one of the variables, and then delta x with respect to r, which is the other variable. And again, at the bottom, we've got the same, it's basically the function for y, so delta y with respect to delta theta and delta y with respect to delta r. And of course, we could have done these the other way round with doing delta r first and then delta theta, and it wouldn't matter as long as we're completely consistent throughout all the calculations that that's the where things are in the notation. So we've got x and we've got y. We can easily calculate these 4 terms. So we look at the expression, basically delta dx d theta is d of theta of r cos theta. So r cos theta is going to go to minus sine theta, and r is just a scaling factor in this case, so it's minus r sine theta. Taking the second term, dx dr is basically taking the differential with respect to r, and in which case cos theta counts as a constant, so r goes to 1 and cos theta is the result there. Third line, we want to differentiate r sine theta with respect to theta, so sine theta goes to cos theta and r is a scaling factor. And then the last line, we differentiate r sine theta with respect to r, and of course r goes to 1 and sine theta is a constant, so it's just a scaling factor that comes out there. So we end up with our simple little tiny Jacobian, minus r sine theta cos theta, r cos theta sine theta. We can also look at differential kinematics for this system as well. So we've already written down what x and y are. We can then differentiate them, and we'll need to use the product rule as well, because we've said that r can change and so can theta. So we have to do the product rule in differentiation. And if we remember, if we differentiate a product of u and v by, this case by differential with respect to x, then we get v times the differential of the first plus the first times the differential of the second terms. So what we're going to do now is look at the first term, x, and we're going to differentiate that with respect to time. So dx dt, that's d dt of r cos theta. So we do this then by using the product rule. So it's going to be dr d theta times cos theta plus r times d dt of cos theta. And what we also have to do with cos theta, so basically we're using the chain rule on the cosine time. So we end up with the following. We end up with dx dt equals dr dt cos theta. We have that term already, and now we've got r sine theta multiplied by d theta dt, because we had to use, because theta is also something which is changing, right? So cos theta, so we have to use the product rule, the chain rule on that one, sorry. Cos theta goes to sine, cos goes to minus sine multiplied by d theta dt. Similarly, we can do the relationship for the y. So we want to know what's the time differential of y. So it's d dt r sine theta. Again, we come back to exactly the same kind of issue. So it's going to be using the product rule, dr dt sine theta times r d dt of sine theta, and of course d dt of sine theta is going to be cos theta d theta dt, because again we have to use the chain rule on that in order to actually evaluate it, because sine theta and theta is not a constant and something that's changing with time. So we end up with the two expressions, and we can write that then in matrix form. And what we see is, first of all, dx dt is x dot. We can just write that as the velocity in x, and dy dt is y dot. That's the velocity in y. We're going to say we're going to multiply against two variables. They're going to be, one of the variables is going to be d theta dt, which is going to be theta dot. The other one is going to be dr dt, which we're writing as r dot. And we can see here that we can basically write it in terms of this matrix multiplied by this input term. So the input term here now is actually the angular velocity and the rate, and the, if you like, the rate of change of radius with time. So if this was a prismatic joint going in and out, we can deal with that here, because we've actually said it's something that can vary with time. So just to work through it then, so theta dot, that's dx dt, equals minus r sine theta times d theta dt, which is that term, plus cos theta, which is that term, times r dot, which is dr dt. So we've got the first equation. Then we do the second equation, dy dt, that's y dot, equals sine theta, that's this term, times dr dt, that's this bit here, plus r cos theta, that's this term, multiplied by theta dot, which is d theta dt. So we can see that we've solved the equation. And as it turns out, surprise, surprise, this expression is actually the Jacobian that we came up with originally for the radial polar arm. So what we're saying is, working through it from first principles, what we've seen is we can say now, we can relate, using the Jacobian, we can relate the theta dot and the r dot, so the speed of the angular speed and the rate of change of the radius, if we're pushing this thing backwards and forwards, gives us the speed of the endpoint in x and y. Right? So we can also do the inverse kinematics of an arm. So if we have an inverse, that is, we can calculate the inverse relationship here, right? So we can actually take that expression and then write it slightly differently. We multiply both sides by the inverse Jacobian, and this way we can relate on the basis of the output velocity, right, the x dot and the y dot. We multiply by the inverse Jacobian, and we can get out basically the angular velocity at the control joint and the angular velocity of r, the rate of change of basically the speed at which we're changing the length. So if it was a prismatic actuator, it's like the speed at which the radius kind of actuation was going in and out. We can calculate the inverse Jacobian analytically, right? So what we do is we take the Jacobian and we flip over this. Well, we flip over these two terms and we change the sign of the other two, and then we divide by the determinant. Yeah. The other thing we have to do quite a lot is basically force relations, and it's worth pointing out that the torque at the joints is also given by the transpose of the Jacobian times the force, right? So we can all. It's relatively easy to calculate things like the torques we need by the motors. If we know the Jacobian, then we can calculate the inverse Jacobian, and then if we know the force, we can calculate the torques that we need. So it's quite a powerful technique. It's just the Jacobian's a good way of doing lots of interesting analysis with robotics. Now let's do a two-linked Revolute Planar arm and do the Jacobian of that. So it's a little bit more sophisticated. In this case, again, we're just going to write down the expression for x and y. Obviously, we've spent the last so many lectures going through Denevit, Hartenberg, and doing these things from first principles. So you could actually, it could be that if it was a more complicated system, what you'd first do is you say, right, let's work out the endpoint of the system. We'll do the forward kinematics, and I'll look at the position part to get this relationship, what I need for this particular analysis, which is the x and the y in terms of the control parameters. In this arm, of course, we've got L1 and L2 are fixed, so the control parameters are theta and theta 1. Theta 1 and theta 2. So let's calculate the Jacobian. Again, we've got a 2x2 Jacobian matrix because we've got two functions. So we've got x and y, function of x, function of y, and we've got theta 1 and theta 2, in this case being the things which are varying. So we need to calculate dx d theta 1, dx d theta 2, dy d theta 1, dy d theta 2, right? So this is quite easy to do. So dx d theta 1, that's d theta 1 of the first expression up here. And now we know why we were actually calculating, why were we doing calculating differentials of cos theta 1 plus theta 2 and so on. It's so we can actually do this and know the answer is correct. So all we're saying here is L cos theta, right, obviously with respect to theta 1, that goes to minus L1 sine theta 1, right? So the cos theta 1 goes to minus sine theta 1. And the L2 cos theta 1 plus theta 2 goes to minus L2 sine theta 1 plus theta 2. And it's not maybe if you're a mathematician, it's completely obvious that was the case, but otherwise it's nice to work them through and just check that that's actually what you're going to get. So, and then we do the second expression that in x with respect to theta 2, and the expression is almost the same, except obviously the first term has only got theta 1 in it, so we take the differential of that with respect to theta 2, that all disappears, and what we're left with is minus L2 sine theta 1 theta 2. And then we do the y expressions. Okay, so now we've got to do the same thing for the expressions in y, where we have a sine rather than a cosine. Again, differentiate. Sine goes to cosine, that's easy. Sine theta 1 plus theta 2 goes to cos theta 1 plus theta 2 with respect to theta 1. And when we differentiate with respect to theta 2, again, the first expression disappears because it's a constant, and we end up with L2 cosine theta 1 plus theta 2. Right? So we end up with these four expressions, and that will be our matrix, our 2x2 Jacobian matrix that we've calculated. So given we've got the Jacobian matrix, we note that, well, if we want to, we can start substituting stuff back into here, and we notice that the first expression up here, minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2, is actually given by minus y, if we actually go back to what we had before. And this other expression here, right, this L1 cos theta 1 plus L2 cos theta 1 plus theta 2 is actually given by position x. So if we write S12 as the sine of theta 1 and theta 2, C12 as the cos of theta 1 and theta 2, we can also write the solution to the Jacobian down, first of all in terms of what the x and the y are, but also then in terms of this shorthand. So we've got a scaling factor of L2 multiplied by sine theta 1 and theta 2, L2 cosine theta 1 and theta 2. So again, if we want to calculate the endpoint velocities, what we need to do is calculate the Jacobian. So then we can actually calculate this by multiplying the Jacobian with the differentials of our angles with respect to time. So we've got the Jacobian. So we can pop in our values. We're not working it all out from first principles again like we did last time. What we see now is we've got x dot and y dot equal the Jacobian matrix multiplied by theta 1 dot and theta 2 dot. So this is a way of relating angular speed at the joints to endpoint speed. And again, this is often going to be simplified using S1 for sine theta 1, C1 for cos theta 1, S12 for sine theta 1 plus theta 2, C12 cos theta 1 plus theta 2. If we have an invertible Jacobian matrix, then we can also calculate the angular velocities given the endpoint velocity. So we could say, if you want to move the robot at a certain speed at its endpoint, you can work out how fast the joints have got to be turning round. And in this case, of course, what we have to do is calculate the inverse of the Jacobian matrix. So you switch over the A and D terms, and you change the sign of others, and then you divide by the Jacobian. And in this case, the determinant, of course, it's just going to be A times D minus B times C, right? As it always is. Again, there's a torque relationship, so you can also relate with the Jacobian the force at the end point. You multiply that by the transposed Jacobian, and you end up the torque vector as well. So that's a very useful thing to be able to do in order to know, what are the torques that you're going to need for a certain loading on your system.